Christian Goldbach was born to a pastor in Germany in 1690. He studied at the Royal Albertus University, and after finishing his studies he went on an educational voyage from 1710 to 1724 through Europe, where he met and was influenced by many famous mathematicians like Gottfried Leibniz, Leonhard Euler, and Nicolas Bernoulli. Back in Konigsberg, he got acquainted with George Bernard Bilfinger and Jacob Hermann, two more prominent mathematicians. In 1725, the German mathematician worked as a professor of mathematics and history at the St. Petersburg Academy of the Sciences. In 1728, when Peter II became the Tsar of Russia, Goldbach became his tutor. Goldbach was also able to write in both Latin and German. He worked on many theorems and ideas in the mathematical world, like the Goldbach-Euler theorem. Goldbach is mainly known for his own conjecture, Goldbach's conjecture. Goldbach's conjecture is one of the oldest problems that has yet to be solved or proved in the number theory in all of mathematics. In 1742, Goldbach wrote a letter to Leonhard Euler, a Swiss mathematician who'd made important and influential discoveries in many branches of mathematics like infinitesimal calculus and graph theory, in which he proposed the conjecture that every integer which can be written as the sum of two primes can also be written as the sum of as many primes as one wishes, until all terms are units. Later on in his letter, he proposed a second conjecture. Every integer greater than 2 can be written as the sum of 3 primes.
With Goldbach's conjecture, numbers can be written and organized in a certain way. This way is called Goldbach's number. In this form, a positive integer can be expressed as the sum of two odd prime numbers. The number can also be expressed as a Goldbach partition. In this form of expression, a given even number can be represented as a sum of two primes. Here are some examples. 6 is equal to the sum of 3 plus 3. 8 is equal to the sum of 3 plus 5. 10 is equal to the sums of either 3 plus 7 or 5 plus 5. And 12 is equal to the sum of 7 plus 5. The conjecture has been shown to hold for all integers less than 4 times 10 to the 18th, but remains unproven despite considerable effort. Since 4 is the only even number greater than 2 that requires the even prime 2 in order to be written as the sum of two primes, another form of the statement of Goldbach's conjecture is that all even integers greater than 4 are Goldbach's numbers.
Even integers from 4 to 28 as sums of two primes. Even integers correspond to the horizontal lines. For each prime, there are two oblique lines, one red and one blue. The sums of the two primes are the intersections of one red and one blue line, marked by a circle. Thus, the circles on a given horizontal line give all partitions of the corresponding even integer into two primes.
So a conjecture is something that people think is true, but cannot be proven like a theorem. So in Goldbach's conjecture, it states that every even integer greater than 4 can be written as the sum of two prime numbers. So first we're going to look at all pairs of prime numbers whose sum adds up to 36. So in order to take a better look at this and how Goldbach's conjecture works, that states at least that there's one set of prime numbers greater than 4 that add up to 36. We're going to look at 36 and all the prime factors. So if we look closely at it, in order to get 36 within 2, which is the first prime number, we'd have to have 34, which is not a prime number, so 2 doesn't work. 3, we would need 33, and 33 is not a prime number, so that doesn't work. 5 is a prime number. 5 plus 31, which is also a prime number, works. So 5 and 31 do work. And then 7 and 29 work as well. So that is another pair of 2 prime numbers whose sum adds up to 36. And then, so 11 does not work. And then the next number is 13. In order to get to 36, we need to add 23, which is also a prime number, so that works. 3. And then we have 17 left and 19 left, which are both prime numbers, and they add up to 17. The conjecture states that there is at least one set of prime numbers that add up to a given sum, and we see for 36 that we have 4 sets of prime numbers that add up to 36.